This is next episode of our lovely track seminar for mathematical physics, and I'm really happy I can introduce our kind guest speaker for today, who is appearing in a cyberspace for this time. This is nobody else than Fridrich Valach, also known as Fritzo, who came to us from the University of Hertfordshire, and Fritzo is nice enough to bring us a very nice topic, and it's nothing but Courant algebroids and full supergravity. So we're excited at this moment, and we can start this session.
Thank you. So, hello, welcome everyone. Greetings from the cyberspace. So today, I assume that you see the screen all that. If you don't, or you see any problems, then just let me know. Okay, so I would like to talk about our newest work that I forgot to write down the archive number, but it's the newest work together with Julian Kupka and Charlie Strickland Constable. And presumably at the end, when I will discuss special cases, I will also touch upon the paper which was preceding this one, which is also maybe of interest to the audience, maybe. Let's see. So, okay, so what is the idea here? So, Courant algebroids or generalized geometry have been used for several decades already in order to understand supergravity or various corners. Actually, more generally, various corners of string theory, from the study of the sigma model to the study of supergravity. And usually these things have been done to like the lowest order in fermionic variables, and occasionally to like the medium order. And so what we did in this work was that we kind of pushed it to all orders, and it turns out that it's actually surprisingly simple, and it was kind of a bit of a surprise that it works. So okay, so let me start with an introduction. So, or like, what is the idea? Okay, so this is kind of the general kind of physics whatever introduction. So first of all, supergravity. So what you should imagine this is. So this is a field theory where your fields include the metric. So there is some gravity in it. Metric tensor is a variable, and it has as its symmetry a local supersymmetry. So local supersymmetry is one of the symmetries. Local supersymmetry. This is essentially the definition of supergravity. And so these things exist in various dimensions. And due to some physical folklore, it's kind of, usually people say that they exist up to 11 dimensions, because otherwise there is some problems that stem from some combination of representation theory and quantum field theoretic considerations. And these kind of higher dimensional supergravities, they do appear nicely from string theory in the following way. So just string theory. So string theory, superstring theory, has several flavors. So let me draw it like this. So there is this type 2. Okay. Type 2A, type 2B. There is type 1. And there is heterotic. And the heterotic comes in two flavors. So there is two heterotic ones. So people say that there is like 5 superstring theories. And then on top of that, we also have, well, we have the M theory, which is some other stuff. So you don't need to know what these things are. It's just that what I want to argue is that, okay, so now if you look at any of these 5 theories and you look at their low energy effective limit, so you look at the dynamics of the lightest sector, of the lightest particles, lightest fields, then what you get is a supergravity. And in each of these cases, you get some kind of supergravity. So for this one, you recover something that's like 10-dimensional n equal 2 supergravity. So 10-dimensional means that it lives in, well, on a manifold which is 10-dimensional. N equal 2 means that it has like supersymmetry counts in various amounts, and this is like you get like 2 supersymmetries. You get a similar thing here, but a different one. So these are kind of the two different n equal 2 things in 10 dimensions. This one leads to 10d n equal 1. This one actually together with heterotic, and this is what I will focus on today. The low energy the low energy limit of these things is the gauged n equal 1 10-dimensional supergravity up to some small subtlety that I will probably not discuss. And for M theory, we get 11-dimensional supergravity. You can say n equal 1. And so what is known in string theory is that this thing is kind of like the highest dimension possible for carrying a well-defined supergravity theory. And this is completely unique. So there is no, if you want to build a theory which has gravity and local supersymmetry in 10 dimensions, in 11 dimensions, then there is only one this option. There is like no, up to a scale, the whole action is fixed. And the same thing happens here. Like there is this n equal 2 is the maximal amount of supersymmetry in 10 dimensions. So, and there is these 2 flavors, and that's all. So these are completely fixed. So you can write down the entire action, field content, and transformations, and they are unique. And this has less supersymmetry, so this is kind of less constrained, and this one is not fixed, but it depends on the choice. So this is fixed if you specify Lie algebra. Lie algebra with an invariant pairing. And so having such a choice, you then can write in principle an action, and it's a horribly complicated action, and it's been constructed explicitly in the 80s. And the way people did it is that they first constructed this one, because this one is sort of universally believed to be particularly simple, and then they reduced it down 1 dimension lower, and they got some expression. And just, if you look at the expression with all orders to fermions, and it's like a page or half a page of just like, and that's already a pretty condensed notation. So it's like a horribly complicated thing. And so what I want to argue today is that if you use generalized geometry, then this thing will be just like miraculously simple and still kind of will retain all the interesting features, except that the formula will be just much nicer. Okay, so that's okay. Maybe let me say what the theory is. So this thing here, so the fields of this theory. So this is what I will focus on today. This one. So fields here are the variables. So it's the metric, which here it will be important that it's a Lorentzian signature. So signature 9,1. Otherwise the spinors don't work out right. All right. Then there is a 2 form on your 10-dimensional manifold. There is a gauge field, which locally it's one form valued in the Lie algebra, and there is a scalar field, a function called the dilaton, and then there is some fermions. So there is a thing called usually the dilatino. There is another thing which I will call the capital psi to distinguish it from something that comes later, which is called the gravitino. So this thing is a vector tensor spinor, gravitino, and then there is a gaugino. So this is this is kind of like a friend of this A. So they come sort of together. So so this is kind of the field content, and in terms of generalized geometry, I will just reformulate this in I will kind of package it into some nicer things. Okay, so this is what I am planning to do, and that's all for the idea and introduction. So any questions about these ideological kind of beginnings?
Yes, we have one question.
Can you hear me?
Yes.
Okay, so I'm not an expert on string theory, but I can try to make some match with quantum field theory. So phi, for example, is the one that I should expect to be corresponding to some scalar field, A to some electromagnetic boson interaction particle, and what about B? Is it B somehow corresponding to weakened Stromian interactions or something like that?
Sorry, corresponding to what? Just the last bit?
I was saying that how should I expect B to correspond to some other fundamental interaction in some sense? Because I can see that is some scalar field, A is some vector field, and what about B?
So the string theoretic interpretation of B is that it's like a higher gauge field. So it's a connection, like mathematically, it's a connection on a gerb, and it's the thing that couples to string worldsheet in the same way that the electromagnetic field would couple to a particle. So
Okay.
there is a so in terms of the string worldsheet action, there is a term where you have your string worldsheet, this two-dimensional manifold embedded in your space-time, and you just pull back B and integrate it over the worldsheet. That's kind of how it's like the higher version of the electromagnetic field.
I see. Okay. Thank you very much.
Yeah, and yeah, right. Okay, yeah, and in fact, this A here even it can be like non-abelian in general. So it's like a Young-Mills, not just electromagnetic. So it's a bit more general. Okay. Anyway, so let me now go into the more details. So okay, so and this is how I think it's best to maybe describe it. So let me talk briefly about Courant algebroids in a sort of more accessible way, which means that I will omit some details. So what is this? So definition is that the Courant algebroid consists of a vector bundle. This is a vector bundle. There is a bracket on the space of sections of this vector bundle. So some bilinear operation. There is a pairing on the fibers. And there is a vector bundle map called the anchor. So typically I call it rho, but for reasons to be seen in a moment, here I cannot call it rho, so I will call it A for anchor. So this is a vector bundle map, and this satisfies some axioms. Okay, so if you know what they are, then you know what they are. If you don't know what they are, then it would, well, okay, let me not write them up, but let me give you an example to have something in mind. So kind of, I will be interested in transitive Courant algebroids, which is a subclass of those, and those locally have the following form. So the local description, which is the thing that you can have in mind, is as follows. So you fix a Lie algebra with a pairing, just as above, and maybe just to make the typographics easier, let me use the usual physics cheating and let me call it trace. Okay, so instead of saying pairing of AB, I would say trace AB. But okay, that's just because the formulas will look simpler. And then what you can take as your vector bundle is you take sorry, so this is our Lie algebra, and then you take M to be simply R to the 10, and then you can take this kind of local model. So the tangent bundle, cotangent bundle, and then you have something then you have a trivial bundle where G is in every fiber. Okay, so sections. So this is a bundle whose sections now you can identify with like triples of vector fields, one forms, and functions on M valued in the Lie algebra. And there is a nice bracket on such things. So okay, let me start here.
Could I
Yes.
For a moment?
Yeah.
You find that this is kind of a local model, but manifold M can be in principle anything else than.
Yes. Yeah. The thing I'm going to write. Yeah. Here you can actually forget about this, but locally since I'm doing it locally, then locally it's like R10. So that's like there is no loss of generality. But like you see, the thing is that if you look at this thing, if you take this to be R to the 10, then you can try to glue it together over some contractible patches, and then you can get a yes. So in general, like slightly more generally, you could in the formula that I'm going to write, you can just omit this and just take any M. But even more generally, it doesn't have to be trivial. You know, in this way, it can be associated to some principal bundle, or actually it can be even more general. So yeah, but at least locally, I can always think of it this way: that I just take R10 for simplicity. Yeah. Thanks. Okay, so let me say that if you have a triple of a vector field, one form, and some Lie algebra valued function, then the formula is that you should again get a triple, and first one is that the vector field will be this one. Okay, let me write it. So this thing will be beta minus I y d alpha. So we see that the bracket is not symmetric actually, sorry, not anti-symmetric. And then there is another term which comes from this t d of s. Okay, so this is a function valued in Lie algebra. I hit it with the Deron differential, so it's a one form. Then I pair it with this other function. So this is a number. I mean, it's not a valued in Lie algebra anymore. It's a one form. So this belongs in this one form bit. And then there is a term which looks like this. Okay, again, you are not supposed to remember or keep this in mind. Just to be a bit explicit. So you have like this is how the bracket looks like locally. The last term, this is the bracket of the Lie algebra. And the pairing of two things is the only thing you can do. So you pair one form with vector field, same for the other one, beta with, with y plus beta with x, and then you pair the Lie algebra things together. And the anchor map in this case is, again, the obvious thing. It's just keeping the vector part of the expression. Okay, so this is kind of what the local model will be. But the only thing to keep in mind out of all of what I wrote is essentially just this bit, that you have a bundle which has the tangent bundle combined with the cotangent bundle and some Lie algebra bit. Okay, very good. And so now let me go back to make a partial connection with the supergravity. So let me define a generalized metric. So there is many ways to say this. We'll call it G is an endomorphism. So it's a fiber-wise map from E to E, linear, and it's symmetric. So it's okay, such that G is symmetric with respect to the pairing, and squares to the identity. So it is really a reflection. It's like a fiber-wise reflection. And each time you have such a thing, then if it squares to 1, then you know that it has a plus and minus 1 eigenbundles. So this thing, such a thing, induces a splitting of your, like an orthogonal decomposition of your bundle into orthogonal direct sum of two subbundles. So this will be the plus 1 and this will be the minus 1 eigenbundle. I will call them C plus and C minus. And then, saying this, that the generalized metric is this kind of a very general thing. So I will let me make an assumption here. So we will assume furthermore, we will assume three things to kind of specialize this to the case of interest. So first thing is that that if you restrict the pairing on the Courant algebroid to this subbundle C plus, then this thing has signature 9,1. Second thing is that this thing, if you take the anchor map, then this maps C plus into TM, and I want this to be isomorphism. So this is an isomorphism. And third thing, I want this bundle C plus to be spin. So I want it to admit spinners. Okay, so this is just this puts some mild topological restrictions, but just I want, if you want to be precise, then you need to require this separately. Okay, so these are the three assumptions, and I will assume for generalized metric. So generalized metric is whatever endomorphism which squares to identity is symmetric and satisfies these things for us. And you can show that, to kind of give you a feeling why we want these things. So if you assume essentially the second bit itself implies that in our local model, which remember that it was T plus T star plus some Lie algebra bit, and I want that the anchor map, provides an isomorphism between C plus and Tm. This thing implies, so the condition 2 implies that actually this subbundle has to have a very specific form. Okay. Okay, now coefficient. Okay, this is just a simple calculation, or not even calculation, just for these things. Okay, so in first approximation, let me imagine that this term is not there. So what this thing is saying is that this C plus has to be a graph of this G plus B plus A, essentially. So it kind of sits in this. This is your Tm, and this is schematically the T star M and plus this Lie algebra bit. Then it has to look like this. It has to be a graph of some map from Tm to this thing. This is your C plus, and so that's why it encodes a metric, a 2 form, and something valued in the Lie algebra. Now this thing in the middle, this term that I crossed out, this thing, in principle, you can absorb this into G. You can kind of redefine G to be something else. But I put it here separately because if you put it here, then it follows that this map A is in fact an isometry up to a factor of 2 or something. So so yeah. Okay. So that's why this term is inclusive. That's one way to look at it. So it's kind of for convenience, but it's not really that important. The important thing here is that this generalized metric essentially encodes these 3 fields. So going back to the supergravity story, so in our general geometric formulation, we will have some bosonic field and some fermionic fields. And with the bosonic, there will be 2 bosonic fields. There will be this generalized metric, and in this local model calculation, you see that this thing corresponds to this G, B, and A. Okay, so this is we already encoded these 3 fields in one big object, and if you look at the content here, then there was also a scalar field, so this dilaton. And the way to properly encode dilaton here is terms of a half density. So I will say that sigma is a section of the bundle of half densities. So H is the line bundle of half densities on M. Okay, so these are things such that if you square them, you get a density and you can integrate it. So this is kind of like a square root of your top form, but except this one is defined more generally. And you may ask why half densities, why not like third densities or 2 densities or something? And well, the answer is that these things are kind of very natural from generalized geometric viewpoints, and we will see that in a second. And so how does this thing encode your dilaton field? Well, the correspondence is that if you already have a metric here, then you have a specific half density, which is induced by the metric half density. In coordinates, this is what you would write as like this thing, and then square root of that. So I guess this, but okay. In any case, metric induces a canonical half density, so this is the sigma G. And since it's a line bundle, then any other half density will be a multiple of this thing. And so yeah, and this is how you get the scalar field phi from the half density. So it's essentially like a logarithm of the ratio of sigma with respect to your metric half density. This might look kind of strange and unnatural, but in fact this is quite common in physics literature. Already, if you look at in the beginning of the 90s in Singel's paper on generalized geometry, this is what he's literally doing. He just calls it capital phi, and he says that capital phi squared is a density, which is just to say that sigma is a half density or phi is a half density. So okay, so this is kind of a natural thing to do. Okay, so these are the bosonic fields. Now to talk about fermionic fields. So let me maybe, I assume most of you are familiar with spinors, but let me just say a few words. So I assume that this bundle C plus is spin, which is just some topological condition that ensures that that there are in fact spinors for this thing. So C plus together with this inner product is a vector bundle over M, whose fibers carry a metric of some signature, namely 9,1. And this from representation theory. It is known that okay. So let me call that there is two irreducible representations of the corresponding Clifford algebra. So there is two spinor bundles. So there is spinor bundles. Let me call them S plus and S minus. And these are the things. Well, they carry a representation of the Clifford algebra. In particular, any section of C plus acts naturally on either of these bundles, or on their sum, if you want. Maybe, sorry, let me just say one thing here. Let me use the following notation. So I will denote frames of C plus and C minus by Latin letters and by Greek letters. Okay, so EA and E alpha. So this will be like, this thing will have some local frame EA, and this thing will have some local frame E alpha. And then any such local frame, I mean, any E alpha is a section of of C plus, and hence it acts on the spinors, and this is what physicists would call gamma A. Okay, so you have these gamma matrices, which are essentially the action of elements of the frame on the spinor bundles. So there is this operator gamma A. Okay, there is gamma A, which act on these spinors. In fact, what they do is that they send S plus to S minus and vice versa. So they really act on their sum. And okay, and then also people usually talk about gammas with multiple indices, which is just to say that this is defined as simply taking all these gammas, multiplying them with each other, and then antisymmetrizing. And as one final thing, you can also, there is a natural pairing on the spinors. So if you have like a section, let's say lambda plus of S plus and a section lambda minus of S minus, then there is a natural pairing between them, which is denoted like this. And okay, so for physicists in the audience, I should say that these are like the Majorana-Weil spinors. So they are real, and there is two of them, and they have a natural pairing and action of C plus. Okay, so that was like the shortest possible introduction to spinors. But okay, so now let me go back to this field content. So now, just as we have two bosonic fields, we will have two fermionic fields. One which I will call rho. And this thing will be a section. It will be a section of a spinor bundle. It's a fermionic field. By the way, just to check. Okay, you are still there. Okay. Just to double check that my connection is fine. Okay, so okay, let me write it like this: S plus. Maybe let me emphasize that they come from C plus by saying that this is the spinors for C plus. Tensor with half densities. Okay, so how to read this? So this thing, which we will call De Latino, I guess, or generalized De Latino, is a section of the spinor bundle of this positive one, S plus, with respect to C plus, and it's odd. Okay, so this is the capital pi, this is parity shift. So this is just to say that it's a fermionic field, so it will be anti-commuting. But the crucial thing here is that it's also a half density. This is what you don't usually do in physics, but here it will be kind of important, and it will be part of the reason why it will be so simple in the end. And similarly, we have the De Latino, which I will call by lowercase psi. So this is again a section, and this will be of the other bundle, so S minus, but also tensored with C minus and with half densities. So for physicists in the audience, this thing is a vector spinor, so it has a vector and a spinor index. Now, the crucial observation, which is kind of lurking behind all of this, is that in generalized geometry, this is a spinor with respect to a different bundle than the bundle for which it is a vector. So it's a vector with respect to C minus, and it's a spinor with respect to C plus. which is the reason why when we want to write the higher fermionic terms, then we can write things like, okay, so possible higher terms that one can write. So you can write things like rho bar gamma ABC rho, using the ingredients that I sketched before, and you can have things like this. This is a perfectly well-defined term, but what you cannot do now is you cannot. The important thing here is that this index is different from these indices, so you cannot contract those two things together. So if you look at the old literature on the subject and what people do when they think in terms of the original variables, so non-generalized geometric ones. So if you think of terms of these lambda and psi, then the problem here is that you can also write many other terms. You can, for instance, write like term which looks like, you can imagine that you have like lambda bar, gamma. Here I will use mu nu indices for like whatever space-time. So you can write also things like this, multiplied with things like, okay, this is a capital psi, psi mu, gamma nu, psi rho. So you can imagine lots and lots of terms which look like this, that they have the same index here as they have it in here, and so they can contract them between each other. And that's why in the ordinary approach you have like way too many choices to do. While it turns out that in generalized geometry there is only two terms that you can write that make sense, and this is one of them. All the others are zero or that can be related to these terms. Okay, so hopefully this was not too confusing. The bottom line is that in this approach you have only these four fields, and that there is this distinction that there is a C plus here while there is a C minus here. That's kind of the underlying miracle. Okay, so that would be off from this part, and then now I will just go and describe the action and the symmetries and how to build them using some unique operators. Or are there any questions?
Yeah, we have one question in the audience.
Mike, can you hear me?
Yes.
Yeah, so how much do you care about the choices of splittings? Like, B depends on splitting, and A can be, connected to a splitting as well. So, yeah.
Yeah, I mean, I personally care too much about splittings. Like the argument here is that I mean, you're right. Like you can write this thing in terms of splittings. I don't think it's very crucial for what I'm trying to do. So what I'm trying to do is essentially just to define a thing which works for any Courant algebroid, essentially modulo some assumptions. But the way to connect it to the original supergravity, I will only show this to you on this kind of local patch, and then I will just mumble something that you can just glue things together. So for the way I'm going to present it, it doesn't. It's not crucial. But the theory I'm going to write down holds just works for any Courant algebroids. Like there is no need to have it specified in terms of any splittings or anything. It's just an abstract Courant algebroid, and this thing will just fly as long as it will have a subbundle of some. I will list this later on, or maybe. Thanks. Okay, very good. So now the last part, or the second last part, whatever, about, let's call it just the action. And so this might be of interest to people who are working with generalized geometry and connections. So first, let me say briefly a definition. So a Courant algebroid connection is sort of the analog of ordinary tangent bundle connection, where you just replace tangent bundle by the Courant algebroid. So it's like a map called capital D that goes from R bilinear. It's like an R bilinear map from sections to sections, and such that it satisfies the usual properties that, first of all, I will use it the usual writing that you just say like dx, y, like you have subscript and then subscript and then I think we write next to it. So for instance, if you multiply this thing by a function, then this just goes out for free, as it should. And in case you hit another section and you multiply it by a function, then it goes out, but you get a derivative term. And this is given using the anchor on f and then multiplying b. And on top of this, the Courant algebra has a natural pairing, so you also require that this thing preserves the pairing. Let me just write it like this. Okay, so this is just a sort of natural generalization of a connection to this context. And one remark is that if you have a Courant algebra connection, then such a connection also acts naturally on densities or half densities, or actually any densities of like 3 densities, 1/3, like any lambda densities where lambda is a number. So acts naturally on densities simply by, let me specify it on half densities. So you just take a section U and you want to hit a half density sigma, such as our field from above. And this thing is defined simply by taking your U, mapping it to a vector field using the anchor map, and then taking a lead derivative of the half density, lead derivative in the usual sense of flows and diffeomorphisms, pullbacks. But then you have to compensate it with 1/2 of sigma and then trace of d of u. Okay, so that is just some formula. The important thing is that they have a natural action on half densities. In general, if you would have some lambda densities, then you would just replace it by lambda. Okay, and now another definition. So this is kind of the analog of Levi-Civita for us. So you say that we say that the connection belongs to this class, which I will call LC of G and sigma. So if you specify some generalized metric and some sigma, then we say that this thing belongs there if it preserves both of them. It preserves this thing as an endomorphism, and also it annihilates the sigma using this formula. And now the important claim here, which essentially follows from studying the representation theory, and I think it's first down to Mario Garcia Fernandez, is that such things actually exist always. So this space is non-empty. Unfortunately, it's not like a point. There is a choice more things. So this is not empty. Here, the only thing you have to assuming that the rank of C plus minus is different from 1, which it definitely is in our case. So the bottom line is there exist Levi-Civita connections, and furthermore there exist. Sorry, forgot to. Okay, nobody alerted me. Yes, sorry, and the torsion vanishes, and the torsion of D vanishes. Where I haven't defined the torsion because I forgot to write it down in my notes. But anyway, just believe me that there is a natural analog of the definition of the torsion, and we require that to vanish. Okay, so yeah, so it vanishes. Sorry, it has zero torsion, annihilates generalized metric. That's kind of the usual analog of Levi-Civita, and on top of that, we can also require that it preserves your given half density. But unfortunately, this still doesn't fix it. Now, kind of the crucial claim here is that even though this set is quite large, okay, let me write it in these words. Like there exist expressions. Is a little bit of a anyway. There exist expressions built out of this connection. I will give you an example in a second, which are independent of the representative in that class of the representative in class, which means that they only depend, these expressions, on G and sigma. They don't depend on the explicit choice of D. And the examples of such expressions are there is a scalar curvature. So those who work with Courant algebroids probably recognize this. So this is the scalar curvature. It's been defined by various authors in various ways, essentially all being the same kind of object, but looked at from a different viewpoint. So this is one example. Again, let me not give you an explicit formula because it's not that denominating, but you can write it in terms of, like secondary, whatever, acting with D repeatedly on something to construct some sort of curvature operator and then contracting it and blah, blah, blah. So there is a way to kind of build it out of this. Something that is maybe more kind of concrete is the Dirac operator acting on rho. Okay, so here the Dirac operator is defined simply as gamma A dA. And perhaps I should say that this dA, here I understand it in the, so here I'm kind of using the component notation of the covariant derivatives. So whenever you see something like dA acting on a tensor, whatever BC, then what I really mean by this is that you take your tensor, you hit it with a D to create a new tensor, and then you take then you look at the ABC component of it. Okay, so this is kind of like a handy notation where all the time you kind of work with tensors. All the expressions, all the terms are separately tensorial. So this is just a remark. So this is how I understand things when I write them like this. And here, so the claim here is that whatever D from this class of Levi-Civitas you choose, this thing will be the same for all D's in this Levi-Civita class. So it really depends. So this expression only depends on generalized metric and on sigma, and of course on the rho, but not on the choice of the Levi-Civita connection. And this only works if this rho is a half density. So that's why it was very important that there was this half density bit here and here. Actually, in this case, okay, there is a similar thing on this psi. Recall that this psi actually has an extra C minus index, which I said I will denote it by Greek letters. So let me write it like this: alpha. So these two expressions are completely independent of the representative of the Levi-Civita class, of this Levi-Civita class, and similarly you can write down things like this and things like this. So all these 5 things that I wrote are independent of the representative, and they are in some sense, some people call them unique operators, so that you can. So despite the fact that the fundamental lemma of Riemannian geometry doesn't hold here, that you have like a unique Levi-Civita connection, despite this fact, you can construct some analogs of usual quantities, and they are unique. And in fact, okay, this is just a side remark, these 2 things are in fact also independent of sigma. So these are independent of sigma. So they only depend on generalized metric and on the spinor rho or the spinor psi. But again, this only holds if they're half densities. Okay, so these will be kind of our building blocks from which we can build the action. Let me also maybe mention you can also construct the Ricci tensor, which for us it will be a tensor which has 2 indices, and they will be like, this is like the C plus, this is a C minus. So it's a section of the tensor product of C plus and C minus. And then what you can show, and okay, let me say there's a theorem. You can show that some nice things work. For instance, the analog of the Lichner-Lewis formula. So Dirac squared plus this hitting any spinor. So this is a spinor half density. So this is let me put rho maybe. So this is the same as -1/8 of scalar curvature acting on rho. And there is a similar thing that if you commute the Dirac operator with this thing, then you can recover the Ricci tensor A beta gamma A on rho. Okay, so this is what we show in the paper, and actually I would be quite interested to see if there is an easier way to derive this thing, because the way we did it in the paper is that we just, it's a very brutal explicit calculation in concrete like frames and all that. While the classical proof of this thing in ordinary geometry is like a one-line calculation essentially. But for some subtle reasons, this doesn't carry through to generalized geometry. So if anyone has a good idea about how to do this, then that's kind of like an interesting thing, like how to derive this directly. Okay, so I think I'm at this point we have all the ingredients, so I can just tell you what the action is. So we started a bit later, so just how am I doing with time? I don't have much more to say, but like, do I have like 10 minutes?
Yeah, of course, 10 minutes is perfectly for us.
Okay. So let me write you the action now directly. So the action, which depends on the generalized metric sigma and on these two spinors, rho and psi. It looks as follows. So integral. First, you have an Einstein term, kind of in this stringy writing. So you have a scalar curvature, which is a function, and you multiply it by this half density squared. This is the one which classically corresponds to the bosonic part of the string low energy effective action. So this is actually the whole of the bosonic bit. So this is the thing that if you write it down fully, it has like ordinary Einstein-Hilbert term. It has like dB, wedge star dB. It has like kinetic term for the dilaton, and it has a whatever Young-Mills kinetic term, and I think that's it. Yeah. So this is all hidden inside this one expression, and this has been known, of course, for a long time. So this is not new, but this is a starting point. What has also been known for now, maybe it's like 13 years, is how to write down the low order part of the fermionic part of the lowest order kinetic terms for the fermions, and they look as follows. So remember that both these psi's are half densities. So together this is a density, and we can again integrate it naturally over the manifold. This is the kinetic term for psi. There is a kinetic term for rho, and there is this slightly surprising but not too harmful term where I use this kind of things. So there is like a cross term. So this has been known. Now our kind of contribution is that we figured out the higher fermionic terms, and it turns out that there is two, because there is only two expressions that one can write up to the coefficients. And the coefficient looks scary, but this is just like 1/3. I mean, the denominator is just 3 times some power of 2. So for supergravity people, these are kind of like easy coefficients. As long as there is like no 7 and whatever 13 things like this, then all is good. This is one term, and the other one is okay. Okay, so there is a term which has 2 psi's, 2 rhos, and there is a term which has 4 psi's. And you may ask, like, okay, so I'm claiming these are the only things that you can write down. Like, there is nothing else that's compatible with generalized geometry that you can write down. You may ask, what about the term which has 4 rhos in it? And well, the answer is that one vanishes, because I mean, the thing I wrote might look sort of simple, maybe in some way, but the point of it is that these terms which are 4th order in spinors, they like they're in general there is many ways how you can write them, and there are non-trivial constraints on the space of all such expressions, which are the so-called Fierce identities. So it's very hard to, if someone gives you like two different expressions, both of them quartic in fermions, it's very hard to figure out whether they're actually the same or not. And one of the, and this is kind of the reason why if I would just replace this thing here by rho and this thing by rho, then this thing would be just 0, although it's not immediate from what I wrote, but like there is this, again, this Fridrich identities, there is some representation theory constraints, and one has to take all into account. So that's why it's like, although it's just 2 terms, it's actually quite involved to come up with them and to check that that's all, and yeah, whatever. Okay, so this is the action, and the supersymmetry transformations look as follows. So again, epsilon is this odd parameter. It will be now the negative chirality spinner and the half density. And the way supersymmetry acts is that it changes this endomorphism G by following epsilon bar gamma A psi B, while the other bits are the first order, this thing, and alpha beta are 0. So it's only the plus minus bit that gets deformed. This is not too important. The half density transforms in a way that it involves the Latino. I didn't say that before, but this thing should be an invertible half density, so there should be no everywhere non-vanishing. So sigma everywhere non-zero. Yeah, as you can see here. Okay, that's why I'm using this sigma -1, sigma -2. And then this thing is given by this, and what we figured out is that there is actually only one term that you can write here, and it has a coefficient like this. And incidentally, when I say that we've derived this or we figured out, what I really mean is that we just wrote down the most general expression that you can write, including the supersymmetry transformations, and then we checked that the action is invariant under the supersymmetry transformations for these choices of coefficients. That's kind of the proof of it. And this thing took us 1 year to actually do, because it's deceptively, well, it's a bit more difficult than it looks. Okay, alpha rho, and then there is another term. And that's it. Gamma C, gamma C rho. Okay, and now the final claim is that the action is invariant under these transformations. So for the proof, you can look into our paper. The surprising thing is that once you figure out all the little details and calculations, and it only takes a couple of pages of calculation. But to come up with it, it took us a year roughly, because these Fierce identities that I mentioned before, it provides some constraints in the space of these quartic fermionic terms. They are sort of relatively nasty to figure out. I mean, you can do them, but we kind of relied on some software to do it for us, and it turns out that the software was cheating us, or possibly we were missing something. I don't know. It was kind of splitting out wrong coefficients, and for some time thought that this thing is just not working, and then we just decided to do everything by hand, and then it worked. But it took a non-trivial amount of time to figure this out. The point, it might not look like it when you look like this. This is like roughly like 5 to 10 times simpler than the usual treatment, and it's like it has some amazing things, such as only gamma 3s appear here. There is no higher terms of there is only terms like this appearing, and that's kind of cute. And okay, so this is the claim that this is the action for n equal 1, d equal 10 gauge supergravity. And maybe just as a final note, so let me say that there is like now what can you do with this? So you can take some interesting limits. So before I said that we will impose these 3 conditions on the generalized metric. it has some specific signature, that it's spin, and that whatever is an isomorphism. Well, it turns out that the only thing you really need is this condition, and okay, the fact that it's spin, and you can relax this middle one. We included the middle one. The middle condition here was included for the purpose of recovering the usual fields. So if you relax this condition too, then you can get some like weird theories which have nothing to do with ordinary supergravity. And in particular, you can study setups where your generalized metric, the subbundle C plus, is everything. So this is the same as to say that this G is identity, which is a very strange thing because there is no metric, there is no B field, there is no connection, there is no nothing. But the theory, the formula that I wrote here are perfectly meaningful, and you get an interesting action which only has two fields, a sigma and a rho, and the only action, the action reduces down to just this thing, and the supersymmetry transformation become just this guy, and this thing is okay. So this is the whole theory, and interestingly, this, although it looks kind of silly, it only has two fields. This thing turns out, this thing becomes what is called the generating Dirac operator. Generating Dirac, if you have heard about it. This thing is the square of the generating Dirac operator up to some coefficients. And this theory is topological, and we studied it in the preceding paper, and we call it the dilatonic supergravity, because the only field that you have there is the dilaton and dilatino, dilatonic supergravity. And although looking simple, you can show that actually the symmetry algebra of this theory is very much reminiscent of the symmetry algebra of the full supergravity. And you can even push it forward to an extent where you can write down a BV action for this theory, and we did that in the paper. So you get this is like a very nice BV, like a theory for which you have like a full BV description, classical BV description, and it's like it has all the ingredients that they usually want. Like it's like it's non-trivial in a sense that it's like it doesn't, symmetries don't close off shell, so it's like a soft whatever algebra. It has high reducibility, so it has like all these kind of nasty things, but in like the very good manner. So it's a very good playground to study things. It's also topological. So that's like one limit, and the other limit is that if you can take your manifold M to be simply a point, and in that case, all these formulas remain. So you still have all the four fields. The integral just drops out because it's just over a point. And you get a fully algebraic thing, no derivatives, and the field space is finite dimensional. But the formula for the transformation of things are still non-trivial. So there is like, including these Dirac operators and all that, they still are non-zero, although they are not like derivatives, but they are somewhat constructed out of your Lie algebra structure coefficients. So so you get another interesting toy model, but this time also including gravity and gravity in the end and all that. So okay, that's essentially the end. And one thing I wanted to cheat, I wanted to kind of show you that how to. Okay, this I will not write. I will just copy it. So this is how if you reduce the theory that I wrote down in terms of ordinary variables, in terms of like G, B, A, phi, rho, blah, 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 then the theory looks like this, just to give you an impression. And now the kind of the astonishing thing is that this is still simpler than, even if you reduce it down and write it in a way that doesn't have generalized geometry, so this is kind of ordinary variables, this is still simpler than the formulas that I know from the 80s, where people derive this thing by reducing 11D. Although it might look like complicated, it's still simpler. So in this way, it's like a way you can use generalized geometry to even get the result that simplifies the stuff in the ordinary context. Okay, and that's where I wanted to end up. So yeah, thank you very much for your attention. Sorry for, I hope I didn't go too much over time.
Cool. Thank you very much. Insights how to ease computations, but still there are many formulas and maybe many questions in the audience. So let me open the space for your questions.
maybe I have some silly questions. So can you hear me? Can you hear me?
Yes, a little, yeah, essentially yes.
So if you can come back to the action that you had about, or even this one, it's fine. I mean, this is a question from someone that really doesn't know so much about this. So this integral that you are considering over m,
Yes.
how should I understand this? Because
In what?
I have some notions from quantum field theory, and one usually does integrate over some field of space, some space of fields, right? So you have this large measure, which is made up by the product of the single measures that you have on fields.
Right. No. This is not integral over the field space. Sorry, if I this is just the classical action of the theory. So this is the integral over the. So all the ingredients are fields over m, and you're integrating over m. So this is just the action function of the theory. So in the path integral, you would need to like integrate over rho sigma g psi and then this thing. But here I'm just working on the classical level. So this is just the classical action for the supergravity.
And from the invariance under the transformation that you have written below, are you also able to recover some Euler-Lagrange equations from this action?
The Euler-Lagrange equations just yeah, I mean you can just derive them directly by varying this functional. It's kind of straightforward and they are not very illuminating. I suppose they should be. I mean, usually in supersymmetric field theories, you have this thing that if you have supersymmetric backgrounds and they should satisfy equations of motion. I didn't check that here, but I think this, whatever is true in the usual supergravity sense should also be true here. So there should be a way to relate these things to supergravity equations of motion, I guess. But anyway, yeah, it's just the usual things work that work in supergravity.
Okay, thank you.
Thank you.
Could you say briefly where the dimension 10 does occur in your secret computations?
Sorry, I didn't catch.
Why the dimension T 10 is necessary?
Yeah, very good question. Thank you. Yeah, I forgot to stress that bit. So first of all, so there is 2 points. One of them is that what is really necessary for this action and transformations, what is really necessary for this to work, I mean for this theorem to work, is that this C plus essentially has to have a specific dimension, and the reason for that is that okay, so how should I say it? So this rank is special because this signature is special because this is the case where we have both Majorana and Weil spinners. I mean, we have Majorana and Weil spinners. So chiral, sorry, we have like real. We have two irreducible real representations of the algebra, and this is kind of the only case in which some of these fields identities hold. So I guess one thing that you use throughout the derivation is
reasons for the spinors and coincidences in low dimension for spin 4, SU2, etc. So no, there can be also problems with renormalization. So it is also told that these theories in dimension 10 are renormalizable in the sense that some integral converges. But certain integrals converge. Which can
well, sorry. Yeah, so I'm not sure. I mean, the stuff that I did was just classical. This was just like rewriting the standard supergravity in 10 dimensions. So this is like a classical story. So far there is no renormalization there. But the reason for this signature is that it's just purely representational theoretic, essentially. That there are some identities that only hold in this dimension. So for instance, if I remember correctly, so there is one of the crucial things to show this thing, and it even pops out when you do it here in this kind of simple setup. You need the identity which says that how does this work? I think it's something like that. If you have ABC, you want that this thing paired with anything, this is 0. So you want such an identity, and this only holds up to, like, it doesn't hold in higher than 10 dimensions. The reason being that this is kind of implied by the fact that if you take your spinor representation, S plus, let's say, and you take the third symmetric power of it, okay, so this is different S, so this is like the third symmetric power of this representation, then this should not, how does this work? Sorry, this another one. Yes, so this thing should not contain S minus as a sub-representation or something like this. Like there is like this fact that you kind of, if you take the third symmetric power of this particular representation of your group, which is SO 9,1 or spin 9,1, that this thing should not sit inside. And it turns out that it does if you go to higher dimensions. So kind of 10 dimensions is the borderline case where this holds. So this is kind of like a representational theoretic viewpoint on the things, but like in string theory, is like people have different arguments of why does this have to be 10 dimensional?
Yeah, so the groups are real spin groups. As
yes.
Like a real representation on complex vector space.
Yes, these are real spinor representations of the. So yeah, this is like spin 9,1 has two irreducible real representations. The Majorana-Weil spinors. That's the only reason why we need this here. So that some representational theoretic things hold. So the classical part, like for people who studied the general geometry, like this bit holds in arbitrary dimensions. So you can write like this bosonic part of supergravity in any dimension that you want. But if you want to kind of complete it to a full fermionic description, then that only works in 10D.
No, I understood that this is sufficient. It is also necessary, this position. On
so
a subset of the sub-representation of third symmetric power of S plus.
I think there might be more things, but this is the one that I remember. This is the one that I think was kind of easy to state. This is the thing that is in there. So in fact, the interesting thing is that like you can in fact. Apart from 9,1, you can also take spin 5,5 or spin 1,9, and they also work because all these things work modulo 8. And so those two are also fine actually. So you can like the whole theory you can write it down even for these groups.
Thanks.
Thank you. Yeah, that was a good question.
Okay, any other question? I would have maybe a question concerning your statement that you built the maximum possible terms which are available, and you created this with some elementary building blocks. Could you persuade me that no other elementary building block can exist? Or
Okay, so very good. Yeah, this is a little bit of like a Lego playing, so I kind of like this bit. So you have the thing is that you have two spinors. You have rho and you have psi, and psi alpha. This one carries an extra index, and you want to write a term which has 4 fermions, and you know that both of them are chiral, so they are like this is in S plus. This is the positive and this is negative, and you know that gamma matrices exchange S like one, like if you would hit this with a gamma matrix, then it would be in S minus and all that, and so it turns out that the only Okay, I see. So first of all, you can imagine that you have like rho psi, etc. Rho psi psi, rho psi psi psi, and or psi. But since this thing carries an alpha index, this Greek index, and nothing else contains these Greek indices, then you have to have an even number of psi's. So this thing goes away and this thing goes away. Now it turns out that you cannot write anything. There is no, essentially because of this identity, there is no term that you can write with 4 things. So there is no scalar in the symmetric product of 4 chiral spinors. So this thing goes away. So you have these two terms. And now you can imagine that you have like terms like, I don't know, rho, something, some number of gamma matrices psi, rho, some number of gamma matrices psi. So the ordering matters, but fortunately you can use Fields identities to exchange these two things. So you can always bring it in a form that has like rho bar something rho, psi bar something psi. So you can always bring them in this form for some number of gamma matrices in between. Or in this case, you can always bring it in a form where you have psi something, psi alpha, psi beta, psi beta. So these are the only 2 things that you can actually have. And just from the representation, from looking at the number of gamma matrices, there has to be an odd number of gamma matrices here, because otherwise it would be 0, because you always pair S plus with S minus. And because it's the same field here and here, it turns out that you can this thing can only be 3 or 7, like gamma 3 or gamma 7. So like gamma with 3 indices or gamma with 7 indices, whatever, 7 indices. Otherwise, this is 0 by symmetric reasons. And finally, you know that because the field is chiral, then you can actually exchange the gamma 7 for gamma 3. So that's why the only thing that you have is the gamma 3 here, and it has to be contracted with the gamma here, and these are the only 2 terms that you have. So it's kind of very lightning. But sorry?
Sorry for interruption. When it comes to derivatives, you claim that you have some class of objects which are invariant under some conditions. When you choose a different representative, it gives you the same answer. And this is another part of this story, how to build this, to show that this building blocks together with the derivatives are independent on the choice of your representative in the class of all derivatives which have zero torsion and some vanishing conditions met.
Mm-hmm.
So this is
Yes. But what do you want to, like? Sorry, what was the question? Or what was the comment?
My formal question actually concerns the argument of why we actually can state that terms with the derivatives fully exhaust all such.
So you are asking what is the analogous argument for the 2 fermion terms, right?
Not really.
Like,
I just wonder when you wrote all 4 or 5 terms with your derivative with some particular choice of your representative in the possible such connections. You claim that nothing but these 2 terms can be used. Fine.
You mean here? Like you want to see this thing as sort of building blocks?
Yes, exactly.
Yes, right. So there I don't have like a theorem which would say that like these are the only things that you can write down. So the argument that I try to argue below, that this is the only 2 terms, that's kind of the stuff that holds for higher fermion terms. So that concerns these ones. So the argument for these things, that why are those things here, is that we simply took them from an older paper which derived that this is actually if you write down the usual known expressions for this n equal 1, d equal 10 supergravity, then it's known that the kinetic terms of the fermions can be written in this way. So this was kind of known. So there I have no claims to like this is the only 3 terms, but I think that those are the only 3 terms that you can write actually. Yeah, but there the argument was more like down to earth. There we just like we already knew that, so we were just like figuring out the higher fermion terms. Okay. And the whole impulse came from the realization that actually there is only 2 things that you can write down, which was. And then we were like, yeah, I mean, surely this cannot be true that like this that you can achieve like you can make this fly with just 2 terms. And then after like this 1 year or maybe slightly less than a year, it was like, aha, this actually works. It was kind of.
Happens from time to time. Okay. Any other questions?
Maybe a quick one. Just any outlook on how this works with Poisson-Lie duality?
Yes. Yeah. I promised that in the intro, in the abstract, right? So Poisson-Lie duality is like a thing that was. So essentially, Pavel Shevera introduced exact Courant algebroids in order to study Poisson-Lie duality. So they are kind of naturally tied with generalized geometry. So the bottom line is that if you can formulate stuff in terms of generalized geometry, then it's kind of compatible with Poisson-Lie duality. And the reason is that this Poisson-Lie duality is a statement about pullbacks. So Poisson-Lie duality, whatever that is in this language. It's kind of like mathematically speaking, on the level of supergravity, this corresponds to the fact that you are pulling back. You have 2 Courant algebroids. You have another one, and they are pullbacks of each other in some specific sense. And the claim is that the operators, such as the scalar curvature or the Dirac operators or all of those things, they are actually natural with respect to these pullbacks. And hence, when you have some field configuration here, you pull it back here. And if it satisfies equation of motion here, it will satisfy equation of motion here. And then you can imagine that you have like 2 different pullbacks and they are dual to each other. So, okay, so it's a very hand-wavy way to say that. Okay, so the point is that if you manage to formulate things in terms of stuff that nicely pulls back, then it should be compatible with generalized geometry and with Poisson-Lie duality. And those things here are particularly nice because they are sections of some bundles, apart from the half density bit where you have to work a little bit to kind of argue. But essentially the point is that all of these things are natural objects for generalized geometry, and hence they nicely pull back, and the usual compatibility argument with the duality still flies. But yeah, so or just in one sentence, it's just once you can write it naturally. Once you can write down stuff naturally in terms of generalized geometry, it should sort of automatically imply that it's compatible with Poisson-Lie duality, whatever it means. I don't know. Is that satisfactory? It's apologies for being a bit of a brief answer.
Great, thanks.
Just a brief comment on what you define as a generalized metric. It pretty much resembles some way of generalizing definition of connection via ATIA, because once you restrict yourselves to sections of tangent bundle furnished with the algebra on fiber, and took all such mappings, you obtain all local data for your A fields. So it really in the way of generalizing this to higher stuff, and maybe further clues for how this generalized things in geometry can locally look might be encoded in the generalization of ATIA as well. So
right,
overlap between
At the very least, I know that like you can just you can even suffice with ordinary ATIA in some sense. Like you can say that if you have Courant algebroid, then it's in particular it's a vector bundle with a metric, with a pairing. So you can construct the corresponding principal ON bundle or whatever principal bundle of orthonormal frames. And if you take the if you mod it out by the if you look at space of invariant, you know, the usual thing, like you take the tangent bundle of that bundle and you mod it out by the group, then you can you can say that connections, these Courant algebroid connections are just maps from the Courant algebroid to that ATIA Lie algebroid, which commute with the anchor or something. I forgot. So in some sense you can use like ordinary ATIA Lie algebroid to describe this, but okay, sorry, that maybe goes in a slightly orthogonal direction to what you were saying. So you were saying that this is okay. No, I disregard my comment. So that yeah, you probably mean it in like a higher sense, and that should probably also
not necessarily. You can view this as a local form of connections for a field.
Okay.
It might suggest how this could look in a global picture. Then you reformulate your generalized ATIA from local picture to the global one. Just one.
Mm-hmm. I see. Okay. Yeah, I might. Yeah, I see. I probably have to think about this. Yeah.
Free note of this remark. Unable to add something clever to this. Okay. So any other question? It's not the case. Let me thank the speaker again.
Thank you.
To je dobrá, to je rozšíření normálního ATIA. Ale jako nejde to, on žádný první nejde.